reinforced soil walls. So the retained fill is producing a dynamic thrust, and we want to know its magnitude and location. And the reinforced soil fill itself has an inertial force, some proportion of W that is acting both forwards and backwards. And let's look at the outward acting inertial force. Okay, so now we've got this, and that's an inertial force. Let's call this number 2. Okay, and that's coming not from the retained fill, but that's coming from the reinforced soil, or to be able to call it the reinforced soil mass, maybe, reinforced soil zone. And we'd like to know the magnitude of that. And its location is not so difficult to discern because we'll put it through the centroid of the mass. And the next question then is, these are two very punishing forces. So are we going to actually essentially scale it, might be a nice word to use. Are we going to say, wow, this magnitude, is it the magnitude of the whole block? Or is it the magnitude of some scaled, reduced proportion of the block? Let's go in and put that in pencil, because maybe we're going to say, you know what? That's a punishing, and it is punishing, by the way, that's a punishing mass. Maybe we'll take some proportion of this mass, right? So the magnitude of this influenced by the retained fill, the magnitude of this influenced by the proportion of the reinforced soil mass that we're going to accept as our incremental demand, and we know its location. And then in terms of capacity, sliding's probably going to be our biggest concern. Things may change in the foundation. Witness the group that Amy was in, and you know, are we going to suffer lateral spreading or liquefaction there? There was also the comment as to whether or not we induce excess pore pressures. Let's work on the basis that the fill zone is a good quality backfill soil, well drained, and the world of excess pore pressures we can ignore for purposes of simplification. So there's the incremental demand, and let's drop down to the internal stability and look for the incremental demand here. If we apply the same philosophy, we're looking for oh yeah, now remember, and thank you, has this locus of slip changed? And in design practice we assume it hasn't, and thus we go in and we give this an acceleration and an inertial force, and we want to know the magnitude. And let's call that a third consideration. Now, to get the magnitude of all of these thrusts, we need to assign an acceleration. The magnitude is a function of, amongst other things, the acceleration. And likewise, the magnitude over here is a function of a number of things, including the acceleration. And then finally, let's go to here. This is a function of many things, the mass of the soil, etc., and including acceleration. And getting that acceleration has considerable uncertainty. Would anyone like to postulate what's happening between peak ground acceleration at the base of the structure, or let's call it peak ground acceleration at the site, and then how that may manifest itself. Would anyone just like to open that conversation? You don't need to make a definitive statement on it. And in fact, we probably want to invite Mahdi Taibat into the room for comment. But would anyone like to make a general comment on the challenges or difficulties in assigning an acceleration to some portion of this block, or assigning an acceleration to this assumed unchanged, let's call it active zone in the structure? Can I invite anyone? Would anyone like to make a comment? It's not my intent to put you on the spot, but it's just if anyone's had to give consideration to this in the past, they may want to reflect back on that thinking. Going once, going twice. Okay, no worries. Let me continue. We're going to have some kind of peak ground acceleration. Maybe I'll move this out here. Okay, we're expecting design guidance is either going to advise us or encourage us to retain a specialist who will look at it in the following manner and say, you know what? There's a peak ground acceleration. Right? And these peak ground accelerations can be highly variable. Let me illustrate that by going to this document, the New Zealand Society for Earthquake Engineering Bulletin. They produced a December 2011. Pretty impressive how they rushed out. I mean, the amount of work must have been phenomenal. They rushed out. How many pages are in this? There's page 425, a 400 plus bulletin on everything to do with the liquefaction and rockfall and slope instabilities. And Brendan Bradley, a colleague of Mieszko Trubinowski, they reported on the near surface strong ground motions. And let me turn to that. It looks like it starts at page 181, so we have to subtract that from the 450. Still a bunch of pages, people. But Brendan and Mieszko went through and they looked at all these accelerations, horizontal and vertical accelerations, and the distances between some of these locations are maybe a kilometer, maybe a kilometer and a half, and they documented. Let me just get this around here. This is the point I wanted to make for you. You know, you got peak ground accelerations of 0.21, 0.5, 0.43, 0.37, 1.4 at Heathcote Valley School, an enormous ground acceleration, 0.22. So spatially within the city, even within the city center region, significant variations in peak ground acceleration. So the point I wanted to get across is to establish the value of this peak ground acceleration is going to introduce some uncertainty. And then we may modify that by site factors. We might be invited to address site factors. And then we might be invited, as we move from the acceleration at the base of the structure to the acceleration at the centroid here, or the acceleration at the base of the structure here to the acceleration of the centroid here, we may be invited to put on a wall height factor. And is that going to amplify it, or is that going to reduce the magnitude of the acceleration? And so we end up now in a situation where there's considerable uncertainty, and depending on the magnitude of the peak ground acceleration, it might be that you're going to say these demands are relatively modest, and I can use simplified tools such as Mononobe or Kabe, or this demand is considerable and the height of the structure is very large, and this is a specialist seismic design. And things have changed over time. In 2001, the nature of the profile of the thrust on the back of the wall was different in 2001 to what it is in 2009, where it's assumed uniform and the height of the structure is, and the point of application is halfway up the height, 0.5 H. And the manner in which a proportion of this wall is taken is it's now at 50%. It was a little different previously in 2001. It's now at 50%. But previously to that, there were questions of whether or not both these thrusts would exert their maximum value at the same point in time, or whether you took a proportion of one and a proportion of the other. Okay. And then in terms of the capacity side of it, if you're looking at sliding resistance, as Sarah observed, yes, there'll be vertical and horizontal acceleration, vertical acceleration up and down. And thus the nature of the effective stress will change here, or might you capture that by diminishing the interface friction and allowing yourself only to mobilize a lower proportion of the interface friction here. So that's the system response. Let's put this in. I guess everything here is on the demand side. Oops. But on the capacity side, let's put reduced sliding resistance. Now, strictly, it's not because the interface friction goes down, it's because the normal stress is changing. But we might capture that through a diminished interface friction. And moving to the internal stability, having addressed and determined what this acceleration is, now we have this zone placing an incremental demand of tension. So we find out what the magnitude of this thrust is, and now we have to say, wow, each of these layers takes some proportion of this thrust. So on the demand side, we need to proportionally assign an incremental tension to each layer, right? And again, the way in which that is done has changed over time. In 2001, the thinking was, let's take the magnitude of this thrust and let's divide it between all these layers. And hey, you know what? The longest layer takes more than the shortest layer. And that idea has subsequently been revised in 2009. The inertial thrust. Let's give this a symbol because it's going to help things a little bit. Let's call this PI, an inertial force or an inertial thrust, PI. and now it's divided by the number of layers. Sorry that I've used the same symbol as n up here, so I'm going to redefine this as the number of layers. And thus, today, once you've calculated this, you say each of these layers takes an equal proportion of the magnitude of this inertial thrust. And where's the basis for that? And it's limited. There are one or two. I was trying to pull up the video, but it didn't work for me. But if you go onto YouTube, you can find it relatively quickly. It's a University of Delaware, if I remember correctly, study shake table test, and they did some investigation. And in fact, if you consider the second discussion exercise, there are two parts to that paper. The first part of the discussion exercise looked at the static loading bit, but in fact they then did dynamic loading of those bridge abutments and reported the findings of that as well. So we can do shake table studies, very expensive, very heavy payloads on shake tables. Often we're forced to work at reduced scale. I did some reduced scale shake table testing with Mishko and a colleague of his, Elizabeth Bowman, in New Zealand a number of years ago. The learning objective that I'd like to get across here is one of this: characterizing the system response doesn't lend itself well to codification unless you end up being very, very conservative, okay? And that has been the concern to date, because the seismic performance of many structures has been quite excellent, actually, and that proved to be the case in the Christchurch earthquake as well. There were structures, and there were structures that were loaded with accelerations assigned to sites that maybe about 1 kilometer away from where the structure itself was. So inferring that the peak ground accelerations at the location of the structure could be adequately described by measurements about 1 kilometer away. And there's an element of an if to that. But across the city itself, there's sufficient evidence to make the claim that many retaining walls were loaded in excess of the design code of the day in Christchurch when they were built. And the geosynthetic reinforced soil structures that I visited, and they come in all shapes and sizes. So Gabion facings, lock block facings, full height facing panels, and there are subtleties to those that, excuse me, we could speak to. But let me tell you what I took out of a day looking at these structures was that from a point of view of internal stability, they were performing just fine. The more flexible the structure, the better it seemed to perform. And for that, if I wanted to give you an example of a very flexible structure, I'd talk about a wooden crib retaining wall. They performed very, very well indeed on sites where the foundations didn't compromise behavior. And the most distress that I saw, and this was a take-home message personally, the most distress I saw on geosynthetic retaining walls was external stability analysis, and external stability failure, and external stability failure by sliding. And if I sketch it here, the worst case that I saw, the most dramatic, and it was displacements of maybe 25 centimeters to half a meter or so. But imagine a roadway that's coming down and making a turn. Imagine that roadway is on a slope. and the slope is falling away. And in fact, the slope is going here as well. Let me give the slope lines like this. And the structure, the roadway, is sitting on, in this case, it was Gabion structures, so Gabion blocks. Let's give those Gabion blocks an outside bend there, and I can put in the Gabion structure. And so we're looking at accelerations that caused deformation of these blocks by sliding out on their foundation soils, owing to the outside nature of the bend and the ground surface falling away. In other words, if we were to look at these in profile, if I was to take a profile, through here, I would have something that would look like this. A Gabion structure. It wasn't very high. I think it was 3 blocks high, 3 Gabion blocks high. And the ground actually fell away quite steeply. It was a subdivision on a hilltop. We've got drainage provisions, we've got pavement and a fence. And then 2 lanes of highway, and actually another retaining structure here. If memory serves me correctly, they were timber pile, and then the ground going back up again, and these displaced out, didn't collapse, but displaced out by a distance here, perhaps of 25 centimeters to 50 centimeters. So no concern that I saw in any of the structures I visited that were geosynthetic reinforced, of which there were 3 or 4 in a total number of wall visits of about 10 or so, because of so many different systems that are used. But the issue was one of sliding, where the ground was falling away and the loadings from the slope were probably quite aggressive. But no concerns that I observed for aspects of tensile failure at all. Are there any questions arising from this? Because I want to close on this seismic. I do want to leave it with the learning objective that we bear a responsibility to characterize the manner of the system response and assure ourselves that the manner in which we're quantifying that system response is a credible quantification. And to leave you with concern primarily for external stability analysis. In terms of internal stability analysis, your growing intuition, folks, was actually spot on. There's such a reserve of strength here that failure in tension rarely seen. And actually, if I was to share a final closing comment, there is a tendency amongst owners and informed contractors building structures to extend, if possible, the uppermost layers a little bit further. It's an empirical rule of thumb. It's just that in a seismic zone, if the concern is to try and improve things nicely, you know what, simply just extend the uppermost layers, the upper 1 or 2, I've perhaps been generous showing it as 3, and just extend them as far back as you can, conveniently, given your judgment. And that, folks, would pretty much close on what I wanted to relay to you on reinforced soil walls, including seismic loading. And I wanted to do it in this manner rather than in the 2009 guide try to chase through load and resistant factors and chase through equations and so on. And I decided to do this more with the objective of influencing the way you think. Are there any questions, any observations, any thoughts that you'd like to share from projects that you've either worked on or been aware of, and anything to share as we close on these retaining walls, as we close on the seismic loading, and as we move kind of almost from a right brain to a left brain, because we're going to move from the mechanics-driven reinforced soil to more the flow and seepage-controlled world of filtration and drainage. Going once, going twice. Okay, you're all doing very well. Let's take a 1 minute where you can literally just stretch. I'm going to do the same. Get my shoulders going, and we'll move into the world of filters, drainage, and material properties to inform that. Okay, so please continue with your stretch, and I will tidy up a few pieces of paper here. And in the big picture, we move to this. In order to specify a geosynthetic for a filtration application, to speak to under drains, to speak to prefabricated vertical or wick drains, to look at barrier systems. All of this requires us to have a feeling for the nature of the, let's use the word hydraulic properties. And in switching to this topic, and an interest now, we're almost stepping away from geogrids if they're primarily used as the material of choice in reinforcement of walls and slopes. And we're moving to a world of geotextile filters, on occasion geonets as a preferential drainage medium, or on occasion the very low cross-plane conductivity of a geomembrane. Then our interest switched to